Hi, this begins our discussion of the topics found in Chapter 2. In the course previous to this one, Digital Devices, you learned how to create a logic network that consisted of flip-flops plus combinational gates to solve a problem. That logic network was specific to the problem. If the problem changed, then you had to design a different logic network, meaning that you had to move wires around, change gate choices, and whatnot. There are many examples of this approach in the real world. For example, some of you may have in your PC a high-end graphics card whose only job is to produce high-quality graphics at a very fast rate. Another approach to solving problems using a digital approach is to design a logic network that can be used to solve many different problems. This would be a general purpose logic network. It may not be as efficient in terms of either speed or cost as a special purpose logic network, but hopefully it'd be flexible enough that it can be used to solve multiple problems. So what is a general purpose digital system that can be used to solve multiple problems? That's easy. It's a computer. A computer is a digital system whose operation can be specified via a program. To change the behavior of the computer, we simply change the program. So what the heck is a program? Well, a program is a sequence of binary codes that represent the instructions for the computer. These binary codes are stored in a place that is called the memory of the computer. Every computer will also have external inputs that can be used to alter the behavior of the computer. These external inputs and outputs are known as the I/O section of the computer. Every computer has at least three principal sections. One is control. Control is digital logic that will be used to fetch and execute the computer's instructions. These instructions will be contained in the memory of the computer. Every computer also needs some way of interacting with the external world, and this will be through input and output lines or devices. So let's define a problem that we're going to solve using a digital system. The problem is going to be based upon a phone number, which is going to have, in this format, 7 digits. Y1 through Y3 and Z1 through Z4. The digital system is going to have one external input that we're going to call loc. If loc is true, and loc stands for local, then the system will only display these digits Z1, Z2, Z3, Z4 in order. If loc is false, then we want the system to display in order all 7 digits. We're going to build two different digital systems to solve this problem. One will be a special purpose approach that's going to use a finite state machine. Recall from digital systems that a finite state machine consists of D flip-flops plus combinational logic that control the behavior of the finite state machine. We will also build a very simple programmable computer system that will also solve this particular problem. It will be programmable in that we will be able to change the program to change the sequence. The finite state machine would be special purpose that this hardware will only display a fixed sequence of numbers. This slide shows the algorithmic state machine chart for our finite state machine. We're going to design this finite state machine to display this fixed sequence of numbers 3, 2, 4, 8, 5, 6, 1. This is going to be our first state that we enter on power up, and in this state we're going to check the value of the loc input. If loc is a 0, then we're going to put in our D out outputs the value 3. In the next clock cycle we're going to move to state Y2 and display the value 2. At that point, in each successive clock cycle we're going to display a different number, so we'll display 4, 8, 5, 6, and 1. At this point we'll be finished and we'll go back up to the top and enter this state again. If loc happens to be a 1, then we'll skip these first 3 digits. We'll start by displaying 8, then move to 5, 6, and 1. Note that this finite state machine approach is very efficient at solving this problem. It displays one number per clock, so it takes exactly 7 clocks to display all 7 numbers. Also note that the loc input is only looked at by this finite state machine in this state. Once we get to these states down here, if we change loc, we will not sample the loc input until we get back to state S star. In implementing this finite state machine, one decision we need to make is how many flip-flops, we need to encode the state. The minimum number of flip-flops that we'll need is going to be 3, because 2 to the 3 gives us 8 possible states, and our finite state machine actually has 7. So if we can we can pick some arbitrary encoding using these flip-flops. Here I'm simply using a binary counting order in which state S0 is 000, state Y2 is 001, and so forth. Another encoder we can use is called one-hot encoding, which we use one flip-flop per state. In state S0, this flip-flop would be on. In state Y2, that flip-flop would be on. In state Y3, this would be on. This would require 7 flip-flops. If we use one-hot encoding, we use more D flip-flops, but it simplifies the combinational logic. Binary encoding is going to use the minimum number of flip-flops, but makes the combinational logic more complex. The textbook uses the one-hot encoding method, which means we're going to have 7 flip-flops for the 7 states. If you want to see the combinational logic derivation, see the textbook. We have the one digital input, that's loc. In order to display the digits, we're going to use a 4-bit output bus, and we'll simply display the digit value in binary. So if we want to display the digit 7, we would display 0, 1, 1, and so forth. This slide shows a timing diagram which illustrates finite state machine operation. We have a clock that's going to control operation of our finite state machine, and time is going to increase from left to right. Initially, we have reset asserted. This is a low true reset, so this low condition means it's asserted, and it's going to force us into our initial state, which is S star. Also notice that our loc input is a 0. This means that the first digit we're going to display is going to be Y1, which happens to be 3. When we release reset, then we're going to begin normal operation. So on the next clock edge, the next rising clock edge, we're going to enter our next state of Y2 and display our Y2 digit, which is 2. Then on successive clocks, we're going to enter a new state and display a new digit. So we'll display 4, 8, 5, 6, and 1, at which time we'll be in state Z4 and we'll loop back around to state S star. At this point, S star is going to examine our loc input. During this time, we transition our loc input to a 1. So at this point, we're going to display the digit for Z1, which is going to be 8. Then we're going to move to state Z2. Which is going to be 5 and display 5, then display 6 and display 1. Note that the finite state machine displays a digit every clock, which is as efficient as we can do.